In today's lecture, I'm going to talk about subgradients of convex functions. This is the main concept of this chapter. In calculus, we know about derivatives of differentiable functions, but non-differentiable functions also appear frequently and naturally in many applications of mathematics, and in particular in optimization. And here is an example. This is the absolute value function. The function is non-differentiable at 0, but 0 is very important as far as optimization is concerned, because the function has an absolute minimum at 0. In the 1960s, motivated by applications to optimization problems in which the objective functions are not necessarily differentiable, Moreau, a French mathematician, and Rockefeller, an American mathematician, independently introduced a generalized differentiation concept for convex functions. So in today's lecture, let me go ahead and introduce this concept, and then talk about some examples as well as properties of subgradients. So here is the graph of a non-differentiable function y equals f of x. And as we know, the line through the point x bar f of x bar with slope v has the equation y equals f of x bar is equal to v times x minus x bar, or y is equal to f of x bar plus v times x minus x bar. And this is a line that goes through the point x bar f of x bar. So it has this equation y equals f of x bar plus v times x minus x bar. And this is also called a subtangent line because the graph of this line lies below the graph of the function y equals f of x. That means it satisfies this inequality f of x bar plus v times x minus x bar is less than or equal to f of x for all x in R. Okay, and the collection of all slopes of subtangent lines of the function at x bar is called the subdifferential of the function at this point. Okay, so the subdifferential of the function f at x bar is the collection of all subgradients of the function at this point, or the collection of all slopes of subtangent lines of the function at x bar. Okay, and the situation works similarly in higher dimension. So let me go ahead and give the formal definition of subdifferential or collection of subgradients for convex function. Let f from Rn to the extended real line be a convex function, and let x bar be a point in the domain of the function. What it means here is f of x bar is finite, is less than infinity. Okay, an element v in Rn is called a subgradient of f at x bar if the following inequality is satisfied: if the inner product of v and x minus x bar is less than or equal to f of x minus f of x bar, and this is true for all x in Rn. Okay, and the collection of all subgradients of f at x bar is called the subdifferential of f at x bar, denoted by partial f x bar. Okay. Now I'm going to talk about some examples of subdifferential or collection of subgradients for convex functions. The first example is the absolute value function. As I mentioned earlier, the function is not differentiable at 0. But if we look at the slopes of all subtangent lines for the function at 0, we see that these slopes form the interval minus 1, 1. Okay, so we anticipate that the subdifferential of the function f at 0 is minus 1, 1. Okay, it's the closed interval minus 1, 1. And now I'm going to go ahead and show that this is true. Okay. Consider the function f of x equals the absolute value of x. Here x is in R. Then the subdifferential of the function at 0 is the closed interval minus 1, 1. Okay. Now let me use the definition of subdifferential presented earlier in order to prove this. Okay, so now I'm going to fix any v in the subdifferential of f at the origin. Then we have the following. By the definition, we have the following. Then v times x minus 0, x bar in this situation is 0, is less than or equal to f of x minus f of 0, and this is true for all x in R. Okay. Note that the inner product becomes the usual product because this function is defined on the real line. Okay. So this can be written as follows: v times x is less than or equal to the absolute value of x for all x in R. Okay. Now, because this is true for all x in R, it's true for x equals, for example, plus or minus 1. Okay. Now, because this is true for x equals 1, we have the following: v times 1, which is v, is less than or equal to 1. Okay. Now, this inequality also holds for x equals minus 1. So for x equals minus 1, we have the following: v times minus 1, which is minus v, is less than or equal to the absolute value of minus 1, which is 1. Okay. So then we have that minus 1 is less than or equal to v. Okay. Thus, v belongs to the closed interval minus 1, 1. And hence, the subdifferential of f at 0 is a subset of the closed interval minus 1, 1. Okay? Now, let me continue by showing that the opposite inclusion is also satisfied. Okay? So now I'm gonna fix any v in this interval then we have the following. The absolute value of v is less than or equal to 1. Okay? Now, for any x in R, we have the following. V times x minus 0 is equal to v times x, okay? And it is less than or equal to the absolute value of v times x, because a number is always less than or equal to its absolute value, okay? And this is equal to the absolute value of v times the absolute value of x, and because the absolute value of v is less than or equal to 1, this is less than or equal to the absolute value of x, and I can also write it as the absolute value of x minus the absolute value of 0, which is f of x minus f of 0. So we see that for any v in this interval, v times x minus 0 is less than or equal to f of x minus f of 0 for all x in R. Therefore, v belongs to the subdifferential of f at 0. Okay, and so we have that the closed interval minus 1, 1 is a subset of the subdifferential of f at 0. Okay, so we have proved that actually the subdifferential of the function f at 0 is the closed interval minus 1, 1. Now I'm going to talk about another example of subdifferentials in Rn. Okay, so we consider the following function. Consider the function f of x equals the Euclidean norm of x, and here x is defined in Rn. Okay, and recall that the Euclidean norm of x is given by the square root of x1 square plus so on plus xn square, or is the same as the square root of the inner product of xn itself. Here x is the antipose x1 xn. Okay, now let me go ahead and prove the following. Then the subdifferential of f at the origin is the closed unit ball of Rn, which is the set of all v in Rn, such that norm of v is less than or equal to 1. Okay, in 2 dimensions, this is the closed unit ball. Okay, the ball with center at the origin and radius 1. So this is more general than the previous example. Okay, and now we follow the procedure developed in the previous example in order to prove that this is true. Okay, so now we're going to show that the subdifferential of f at 0 is a subset of b, and b is also a subset of the subdifferential of f at 0. Okay. So I'm going to fix any v in the subdifferential of f at 0. Then by the definition of subdifferential, we have the following. The inner product of v and x minus x bar in this situation is 0 is less than or equal to f of x minus f of 0. This is true for all x in Rn. Okay. Now, by the definition of f of x, we have the following. The inner product of v and x is less than or equal to norm of x for all x in Rn. Okay. Because this is true for all x in Rn, it is true for x equals v. Okay, so for x equals v, we have the following. The inner product of v and v has to be less than or equal to norm v. Okay, so this can be written as norm of v squared is less than or equal to norm of v. Okay, so this implies that norm of v is less than or equal to 1, because in the case where v is 0, for sure this is true. If v is not 0, we can divide both the sides by norm v and obtain this. Or v belongs to the closed unit ball P. Okay, so we have shown that the subdifferential of f at 0 is a subset of B. Okay. Now let me go ahead and prove the opposite inclusion. To prove the opposite inclusion, I'm going to fix any v in the closed unit ball, and then we show that v is in this subdifferential. So fix any v in Rn such that norm of v is less than or equal to 1. Okay, that means v is in B. Then for any x in Rn, we have the following. The inner product of v and x minus 0 is the same as the inner product of v and x. Okay, and by the Cauchy-Schwarz inequality, this is less than or equal to norm of v times norm of x. Okay, and note that norm of v is less than or equal to 1, so this is less than or equal to the norm of x. Okay, because this is less than or equal to 1, and this can be written as f of x minus f of 0, because f of x is norm of x and f of 0 is 0. Okay, so we have seen that v, the inner product of v and x minus 0, is less than or equal to f of x minus f of 0, and this is true for all x in Rn by the definition of subgradients. V here is a subgradient of the function at 0, or v belongs to the subdifferential of the function at 0. Thus, we obtain the opposite inclusion. The closed unit ball at 0, the closed unit ball is a subset of the subdifferential of the function at 0, and we establish this formula. The subdifferential of the norm function at 0 is equal to B. Note that both functions considered in previous examples are of real values. In this example, I'm going to give an example of an extended real value function and its subdifferentials. Okay, so let omega be a non-empty subset of Rn. The indicator function associated with omega is defined by the indicator function of x is 0 if x is in omega, and it is infinity if x does not belong to omega. Okay, So this is an extended real value function, and we can see easily that the domain of the function is omega. Okay, and the AP graph of the indicator function here is omega times this interval. Okay, so in this example, we're gonna prove the following. For any x bar in omega, or for any x bar in the domain of the function, the subdifferential of the indicator function at x bar is equal to the normal cone to omega at x bar. Okay. And recall that the normal cone to omega at x bar is defined by, this is the set of all v in Rn such that the inner product of v and x minus x bar is less than or equal to 0 for all x in omega. Okay? Now, let me go ahead and prove that this is true by the same procedure developed earlier. Okay, so I'm going to fix any v in the subdifferential of the indicator function at x bar. Then, by the definition, we have the following. The inner product of v and x minus x bar is less than or equal to f of x minus f of x bar for all x in Rn. That means this is true for, the inner product of v and x minus x bar is less than or equal to the value of the indicator function at x minus the value of the indicator function at x bar. And this is true for all x in Rn. Okay. Note that x bar is in omega. By the definition, the indicator function, the value of the indicator function at x bar is 0. Okay, so this is 0. So we have the following. The inner product of v and x minus x bar is less than or equal to the value of the indicator function at x, and this is true for all x in Rn. Okay? Because this is true for all x in Rn, it is true for all x in omega. So then we have the following. For any x in omega, we have that the inner product of v and x minus x bar is less than or equal to the value of the indicator function at x. But here we see that x is in omega, so by the definition this is 0. Okay. We obtain the following. The inner product of v and x minus x bar is less than or equal to 0 for all x in omega. By the definition of the normal cone to omega at x bar, we have that v here belongs to the normal cone to omega at x bar. Thus, v belongs to the normal cone to omega at x bar. Okay, the opposite inclusion. So we obtained this inclusion. Okay, and the opposite inclusion can be proved very easily by using the same procedure.